Memories in the beginning, and we talked about volatile and non-volatile memories. So during the class, I believe we talked mostly about testing of RAMs and especially SRAMs and DRAMs, right? And in particular, we talked a lot about the marching tests. So these involve writing patterns into memory and reading them back. But if you are testing any non-volatile memory, then you cannot obviously write anything to the memory. Okay. So, for example, it is a ROM or a PROM or flash memory, etc. So, there, what is usually done is we can have um, a random testing pattern that is written into the memory, right? So, we may be able to use an LFSR. We talked about an LFSR when we talked about logic based. So LFSRs can help us in generating pseudo-random patterns, right? And as far as the address is concerned, we can use a counter. And to control the read write, we can use some sort of a control logic. So we can implement a something like in the increasing order of addresses, right? Write random patterns. Okay, so we will not write random patterns. It won't be write a 0 or a write a 1. It will be write a random pattern. And then we can go back and again read off those whatever we wrote. Right? But this time we don't know what we wrote. Right? It was all random data that we wrote. So the data that is read out, right, can be compressed using what is called as the multiple input signature register. I believe we have mentioned that also. So use a miser to compress the bits that are being read out. And then if you know the contents of the ROM that was supposed to be there, right? If you happen to know that data a priori, then we know what signature we should be able to get from this system. And if it is anything different, then we know that there is a bug, right? We may not be able to find out where the problem is, right? But we will know that there is some, something is wrong with the ROM, some bit is corrupted, right? So this is a sort of a simple, scheme for testing of non non-volatile memories. Okay, you can use ROMs uh, or any other non-volatile memory, and you can test them like this. There are also some simple schemes like you can add all the contents, right? So if you happen to know what the ROM is supposed to store, right, we can keep what is called the checksum, right? So there may be some extra, assume that there is one extra word in the ROM. Okay, this is not supposed to be used for any other data, right? And this is the place available for writing your data. What you could do is you can add up all the values here, right? And assume that you ignore all the carries. Okay, when you are adding, if you are getting carries, just ignore them, and whatever you get, that sum is known as a checksum, and you can store it. And if any one of the ROM bits, gets corrupted, right, then this checksum is very likely to change, right? If there are multiple errors, it may not change, right? But if there are single errors, the checksum is likely to change, and we may be able to use that also as a simple check for whether there is a error in the ROM. So this is a very simple technique that is often used. This may not be as good as the LFSR, MISR based technique. These are a little bit more robust, right? They when there are multiple errors, also this MISR based technique will be able to sort of figure out whether there is a bug. But the checksum based method is not very robust. Okay, is that clear? Any doubts? Any doubts in this? All right. So let us come to the topic that was, supposed to be covered today, right? So today we are going to talk a little bit about system level testing, right? So see, today's systems are fairly complex, right? I mean, we have systems on a chip, right? But in spite of the ability to integrate a lot of functionality into the same chip, we may still need to use a PCB to integrate the system, right? We may not have still reached a stage where the everything that is there on the board can be integrated into the system on a chip, right? For example, it is often very difficult to integrate analog and digital on the same chip. So, for example, if it's a microprocessor or a DSP, we rarely see analog getting integrated into these chips, right? On the other hand, for microcontrollers, we see that analog and mixed signal components are also integrated. So, in order to build a complete system, we will still need maybe other parts, right? Maybe there'll be external memories, maybe external, analog parts like A to D, D to A converters, right? So, to make a complete system, we may need many other parts, and this is an example of a PCB that has been created, right? Today, even PCBs are very complex, right? What is shown here is a perhaps not such a complex PCB. This shows maybe this simple dual inline package, and sockets are available. You can insert the chip into the socket, right? But it is also possible to directly mount the PCB, I'm sorry, the chip on the surface of the PCB and solder it directly to the surface of the PCB. So that is the surface mounted PC chips, right? And here, this particular PCB, you can see the traces of wires on the PCB. Um, y- there was a time when people used to use a single layer of such wires. Okay, so that was called one-sided PCB. Later, they started using dual or double layer PCB. So on the back of the PCB also there used to be wires. Now it is common for PCBs to have multiple layers for wiring, right? So somewhat similar to the way layers of metal are used in a integrated circuit. So there may be many layers of metals, and there may be many layers of routing, right? And they are separated by insulation material, right? So that is how modern PCBs are, right? And to make things even more complicated, see, a complete system may have multiple PCBs mounted in a rack or a stack like this, right? So you may have seen maybe the servers or something like that, right? If you have ever visited the IT server room or something like that, you will see that there may be many stacks of PCBs, like this in a complete system. So you will see that we have chips, right? And inside the chips we have various things like microcontrollers, maybe microprocessors, memories, right? These are all embedded into this chip, right? And many chips are embedded into a PCB, right? Many chips are mounted on a PCB and wired together, and many PCBs are you know uh, connected together to form a complete system. Okay, so there is a great deal of complexity here, right? So there is a principle called rule of 10, which I'm sure somebody would have mentioned to you already. Okay, does anybody know what a rule of 10 is? Has it been mentioned already? If it is mentioned, I will not repeat it again. Anybody knows about the rule of 10? Okay, maybe it has not been mentioned. So let me spend a couple of minutes. So the rule of 10 is a rule about economics of testing, right? So the rule says that the earlier you test and find the defect, the better it is, right? So for example, we could test the chip thoroughly, right? And we may be able to find a defective chip and separate it from the bad chips, right? So we have high quality control, low DPPM, right? And the user who is receiving the order, right? People purchase chips in very large quantities, right? And they integrate them into their system, right? So if there was a chip that was not correctly tested, maybe the fault coverage was not sufficient, or maybe because of some inefficient testing or insufficient testing, the faulty chip found its way into the PCB, right? And now the faulty chip is present in the PCB. You suppose the cost of testing the chip at the IC level is X, right? Then imagine that the faulty chip has gotten into the PCB, and now many PCBs are made in large quantities, right? I mean, people make PCBs also in thousands and tens of thousands, right? Because they want to sell these end products to a large number of customers, and they do test the PCB. But imagine that somehow this faulty IC was not tested at the PCB level also, and it entered the system also, right? See, if X is the cost of testing the chip, then the cost of testing the PCB, right? Um, and detecting where the error is, right? See, if the PCB is tested and then we identify that the problem is actually this particular chip over here, that cost will be 10x, right? And if this PCB also we could not find that defective IC, then this PCB may have gotten into the system, right? When I say system, it could be something like this, right? Or it could be even maybe it found its way into some end product. Okay, maybe the customer has an end product, and that end product may be used somewhere else geographically, in some other city, somewhere it has being used, right? And now the customer may find that it doesn't work, right? And he or she will return that system saying, this is not working. And then it has to find its way into the testing department of the product maker, right? And that person has to verify whether indeed this is a faulty chip, I'm sorry, a faulty system. And he or she must find where the problem is, right? There are so many PCBs, maybe multiple PCBs, and each PCB has many many chips. So to identify where the error is, right, is very difficult. The debugging becomes much more difficult, and the cost may be like 100x. Okay. So this is the rule of 10. The earlier you find the bug or the defect, the better it is, right? So that is the rule of 10. And um, so we will assume that ICs have been tested a priori and all that, right? But in spite of all that, when you make a complete system, right, ICs may still go bad, right? Maybe the way the person is preparing the PCB, right? There may be some soldering problems could be there, or some PCB manufacturing may be there may be some process problem, and as a result, some traces are broken, and there could be short circuits in the wire in the PCB, and the same thing could occur here also, right? You can see how complex the system is, and the systems are typically used in rather harsh conditions, right? If this system is possibly used maybe in a very hot environment or a very cold environment, it may be fitted in a vehicle which is constantly moving and subject to a lot of vibrations. So there may be many harsh conditions the chip has to endure, and it is quite likely that defects may develop over time also. So it is required to sometimes test the system uh, even when it is in operation, right? So people talk about two things. One is called as in-field testing. I think I may have mentioned this to you before. So one is in-field testing, which means that the product is now in the hands of the customer, right? And there is no tester available. There is no expensive equipment available to check whether the PCB or the IC is bad. So some sort of a test must be done, even though we are in the field and we don't have all the equipment with us. The second thing that people talk about is what is called as online testing. So online test refers to testing the system when it is still being used. So if you want to test the system, um, typically we go to what is called as a test mode, and at that time the system cannot function its in the normal mode, right? But if you can do some testing when the system is still operational, that is called as online test. So this has been a big problem with system makers, those who create electronic systems. So earlier they used to use what are called as ad hoc techniques. Okay, so they used to use ad hoc techniques. What is an ad hoc technique? There is no guarantee that it will work everywhere, right? It is some sort of a hack that we have found in order to make our life simpler, right? So you may have seen, some people use jumpers. This used to be the most common way of testing systems a long time ago. So what they will do is, maybe, if this is a connection here, so there will be a jumper wire, okay, and it will be connected like this between these two, making a connection. And you can remove this jumper wire manually. So when you do that, these two get isolated. Okay. So here is a possible way to use it. There are two different chips that talk to one another, and here is a jumper wire. And if you remove this wire, then you can connect an instrument here to see what this circuit is producing. Okay, suppose it was supposed to produce a sinusoidal wave here. You can check on the equipment to see whether it is indeed producing a sine wave. And if that is producing correctly, then the problem could be here, right? Or maybe this is not producing the correct waveform, and as a result, the problem could be, here, right? So we could see whether there is any problem here by connecting a different signal generator. So I could connect a signal generator which gives a proper sine waveform and see whether, given the correct waveform, this circuit will correctly function. So we can get access to the pins, input pin of this IC and the output pin of this IC by disconnect this jumper. And once we are sure that both of them are working, we can close this jumper. Then we can see if there is any other place. So there may be many such jumpers that are placed. So this was a way people used to test, and they would train their employees, right? So if some customer calls that their TV or something is not working, then a person will come to the house with some equipment, right? And they will open the TV, and they will pull out some jumper. They will connect some signal source, and finally figure out what is wrong. And whatever is required to be replaced, they will replace. So this training would be given to these technicians. So that was the technique that had been adopted for many years. Now it is difficult to use these techniques because systems are very complex now, right? Like I told you, there are multiple layers of connections in the PCB. So even if you use jumpers, you can only do it on the top layer. Maybe there are many layers of interconnects that are beneath, and you can't apply all these jumpers and all those kind of things. People also used to use what is called as bed of nails testing. Okay, so there used to be something called as bed of nails testing. This may still be used by some people. Okay, and as the name itself indicates, there will be a sort of a there'll be a contraption which looks like a bed of nails, and you can place it on the PCB, and it will make connections with all the wires underneath. And then you can read off all the signals, and maybe connect it to a digital logic analyzer and see what signals you are getting and things like that. So that is also one particular technique, right? But today, it is common to use what is called as boundary scan. right? So this is called boundary scan. So what motivated people to do this boundary scan technique is, see, there are many different vendors supply chips, right? Intel, TI, analog devices. So there are lots of different vendors that produce these ICs. And if somebody were to make a PCB with ICs from different vendors, right? This may be from Intel, this may be from TI, this some other maybe from analog devices, etc. Then practicing any kind of system level test must have a standard. Okay, without this standard, it becomes very difficult to support of the customers. So all the companies that were making semiconductors got together, and they came up with a standard way of testing the PCBs, and that is this boundary scan, and it is also a standard now. Okay, IEEE 1149.1 standard. Okay, so it requires you to place some additional logic, right? So let us say this is the core of the chip. That means it has all the digital logic, maybe processors, etc. Right? Lot of different things maybe inside. We will add additional cells called boundary scan cells. So these are called boundary scan cells. And the idea will be that in the normal mode of operation, okay, if I want to apply an input to this chip through this pin, it will be possible to apply it directly. And similarly, in the normal mode, maybe the core produces some output, and that can be observed here. It comes here at the output pin. So that is the normal mode of operation, where the input pins directly are available to the inputs of the core, and the outputs of the core are directly available at the system output. But in addition to that path, that is a parallel path, we will also have a serial path like this. So these boundary scan cells will allow a mode in which the test mode in which we can shift in data into these boundary scan cells. So for example, let us say these are the input pins, and let us say I wanted to simulate that, what is it called, the jumper wire, right? So if I have wanted a jumper wire, I would have created a jumper here, and I would have applied some patterns here, right? But now I don't have a jumper wire, but what I can do is, suppose I wanted to apply a 101 pattern here, I can bring the pattern sequentially through this wire known as the test data input, and I can shift in that data here, right? And these could also be input pins. Maybe we wanted 111 here or something like that, right? So we can shift in that pattern, and then we will go into the normal mode. See, now in the normal mode, what we apply here is not reaching these cells. Instead, whatever we brought in from the outside world, those inputs are coming to the core logic. So this may be a test vector. As a matter of fact, there may be a scan chain here. So I may be able to use this path to initialize a scan chain, and I may also be able to initialize all the inputs. Once I have done all that, I can go into the normal mode of operation, and allow the circuit to produce the correct response. Okay, so the maybe the good response happens to be 1 1 0, and a faulty circuit response could be something different. Now, having captured the values into these cells, we can again go and shift out the contents of these cells, and go to what is called as the test data output. So we will need additional pins like test data in and test data out, which were not present in our original design. So we will need extra pins, test data in, test data out. Then we also need a test mode signal, which tells me whether I'm testing the chip or I'm in the normal mode of operation. And we may also need a clock for test purposes, right? So this clock will help me to scan in the data. The boundary scan cells are fed by the test clock, which is different from the clock that is given to the core logic. The core logic may be capable of operating at hundreds of megahertz, but shifting of test data may happen at a slower pace. And sometimes you may also need a test reset pin, right? So this is an optional pin, okay? But the remaining four are mandatory. So whether it is Intel or TI or analog devices or ST Microelectronics or any other company, they will make sure that on their chip there is this test data input, test data output, test clock, and TMS, and they will place all these boundary scan cells, right? And they will place the other registers that are required to be placed as part of boundary scan cells. I'm sorry, boundary scan architecture. And then you can actually then freely use ICs from any company. Okay, so that is why it's a standard. So essential idea is similar to scan. That is why it's called as boundary scan. It's called boundary scan because these bound cells are in the boundary of the chip. It's a boundary scan, right? So once again, this is this explains the same thing, right? So using test data input, you can go and apply the patterns and bring in the required inputs and outputs. I'm sorry, bring in the inputs to the core logic. So this is your core logic. Okay. This is the core logic or application logic, whatever you want to call. And like I said, the TDI may go through. It may be connected to scan chains internally to this core. There may be any scan chains, and we may be able to connect them in this fashion. So it's a slow process, but we will be able to initialize all the scan registers through this TDI TDO. So if this is your PCB, let us say with 4 chips, then what you could do is you could take the TDI and go through all these guys, right? And the TDO of this you can go and use it to. So this is known as the daisy scan architecture, right? So this TDO of this will feed the TDI of this, and the TDO of this will feed the TDI of this, and so on. Right? So at the system level, there is only one TDI and one TDO. So this is one possible way to connect everything together. So this is the so-called daisy chain. Of course, you can do other ways, right? It is up to you. You may want to have a different architecture, right? Where there are multiple TDIs and multiple TDOs. So that is entirely left to the system designer. The IC makers will make sure that TDI and TDO are provided. How you connect them together is your own, will and wish. So you see, imagine that we have to test this chip. Then you can see the test data in, we'll have to go through a very long path like this. Okay, that may be very slow. And in this example, suppose this is the one that is being tested, it will be very bad. You will have to go through all these guys before you get to this. So that is why they have provided this bypass register. So if you don't want to go through all these chains, you can just go through a bypass register and come directly to the output. So you can bypass having to go through the entire boundary scan chain. Okay. So that will be faster. So here is what is inside a boundary scan cell. So this is your, if let us say this, there are in a way there are two kinds of boundary scan cells. You can think of this as an input boundary scan cell, where this is the external input, and that is going to the core of the chip. You can think of this as an output boundary scan cell, where the output of the chip is going to the boundary scan cell, and the output of that is going to the external world. So this could be your uh, input pin, right? This is the data coming from the external world, and this could be the sort of this could go to the core of the chip, or it could be the other way around also, right? We could have the core here and it could be reaching the outside. So there are three modes of operation. So there is the normal mode, where the see, in order to implement this boundary scan cell, there are two D flip flops and two muxes. So there is a, this mux is driven by a signal called load or shift, and this one is driven by a test or normal. So in the normal mode, test or normal is zero. That means it will allow this guy to go directly to this. So there is no, this guy doesn't really bother you. So the boundary scan cell is not coming in the way. The data directly travels to the core logic. And the cell is like transparent to the application logic. The cell doesn't even know that this exists. There could be a scan mode where this guy is set to 1. That means the TDI is the one which is being passed to the multiplexer. And we could do we could clock this flop, and as a result the TDI will go to TDO and things like that. So this could be another, the scan mode. Then there could be a capture mode, where imagine that this is a core logic. Okay, this is a core logic, and it has produced some output, and we want to capture this in this particular cell, right? So we make the shift or load equal to 0. That means the output of the core logic is what is passed to this D, and we will apply a clock to this. So that will capture the output of this data here. I'm sorry, output of the core logic here, and that can be scanned out. So there are many modes of operation. These three are most important: normal mode, scan mode, and capture mode. So is that part clear to everybody? Why we need these modes? Any questions? Okay, I have borrowed these slides from this particular Yonsei University. I felt these slides are very well made. Okay, these are available to you. You can directly go and look at them. So these three things that I mentioned earlier, normal mode, scan mode, and capture mode, are also explained here. So in the normal mode, this flop, I'm sorry, this multiplexer will allow the core logic to send its output directly, or the input to send it data directly to the core. So we can have a core on this side or on this side. If the core is here, then this is an input pin. If the core is here, this is an output pin, right? Here is the normal mode. So assume that this is your, the, I'm sorry, the second one is a scan mode. The second is a scan mode. This is the normal mode. This is a scan mode. So here we want to take this path so that the data that is being scanned in gets captured here and goes out as the same. And this one is the capture mode, right? So the data from the core logic gets captured here, right? Okay, I think I made a mistake. This is the scan mode. Okay, this is the scan mode. Let me write it properly. So this is the normal mode. Normal mode. Okay. So the dark line shows the direction of the data. This is the shift mode, where the data is shifted like this. And this is the capture mode. So the core logic may have produced some output, and we are trying to capture it into this for observation. Okay. And there are many things that we can do with boundary scan. One is known as external testing or X test. So the problem there is we have a chip and there are interconnects between them. And we want to test these interconnects. Now the interconnects may have two problems. One is an open circuit or maybe a short circuit. So how do I test that the circuit is open? Right. So what I'll have to do is imagine that this there is a boundary scan cell here which is driving this wire, and that wire is supposed to be connected to this guy here. And we are worried that this may be open. So what we could try and do is we want to know whether a 0 can go correctly from here to here and a 1 can go correctly from here to here, right? This interconnect does not have an open fault. If I place a 0 and I get a 0, if I place a 1 here and I get a 1 here, then I'm convinced that there is no fault. So what I could do is I could initially place a 0 here. Okay, then I will come and place a 1 here. Then I'll capture that 1 here. So I'll have to go to the shift mode and bring in that 1 to this particular wire. And similarly, I should use the shift mode and bring the 0 to this wire, or rather this boundary scan cell. Then I could do a capture in this boundary scan cell. and then I will go back to the shift mode and see what was captured. So if a one was captured, then I'm convinced that there is no broken wire here. But if this 0 continues to be there, then obviously there is something wrong, right? So similarly, I may want to first scan in a 1 here, and then scan in a 0 here, and then capture and see whether that 0 comes here. Okay, if it doesn't come, there is some problem. Okay, this wire is it could be short circuited. Okay, there may be another wire which contains a 1, and this guy is picking up that 1 from the other wire. So interconnects, they run very closely to one another, and as a result there is a chance of opens and shorts. So in order to test the interconnects, we may apply certain patterns. See, for example, we could start by applying 0 0 0 and check whether the 0 0 0 comes here. Then we can apply a 0 0 1 and see whether everything comes correctly. Then we can apply a 0 1 0, then apply a 0 1 1, then 1 0 0, and 1 0 1, 1 1 0, and 1 1. We apply 8 patterns. So if you take any pair of wires, let us say we take these two wires, look at that, 0 0 has been applied, 0 1 has been applied, 1 0 has been applied, and 1 1 has been applied. If you take these two wires, 0 0 has been applied, 0 1 has been applied, 1 0 and 1 1, right? So take any pairs, even these two. So 0 0 0 1, then 1 0 and 1 1. So this particular pattern, right, allows me to ensure that any pair of wires have been tested with all the binary patterns that could possibly come on those two wires, namely 0 0 0 1 1 0 1. So this is the way usually interconnects are tested. So if I may have 32 wires here. Okay, then I'll have to apply the all those patterns. Okay, so 0 0 0 0 and then 1 1 1, all those patterns may have to be applied to convince ourselves that there are no. So here we are assuming that any wire could be shorted with any other wire, right? Because when you have 32 wires, you may wonder, why should we test, all kinds of combinations? But what could happen is the wires may not be straight forwardly connected like this, right? They may sometimes be routed in different points, and as a result, we don't know who is next to whom. Okay, so it is possible that there is some shuffling around of the wires, and as a result, any wire could be in the neighborhood of any other wire, right? That is the reason why we may have to apply quite a few faults. So this is called as external test or wire test. Is that clear? Any doubts? Function of second flip-flop. Yeah, yeah. So the external test is applied, like this. So this is the interconnect between the two ICs. So this is one IC and this is another IC. This is the output boundary scan cell and this is the input boundary scan cell. And there may be core logic here and there may be core logic here. And I will use the shift mode to bring in whatever data I want, right? So now I hope the reason for having the second flip flop is clear, right? So I will need to drive this guy, which I can do through this. Now the mode will be one. We will keep that data in this second flip flop. Similarly, I will have brought in the, suppose I bring a 1 here. Before I bring the 1 here, I should bring the 0 here. And once I capture, I can see whether the 1 from here gets captured here, or whether the old value of 0 is still here because there was a break in the line or something like that. Right? So that is what I hope the reason for adding this extra flip flop is clear. We can also have another called kind of test called as an internal test, right? Or in test. The idea here is to test the chip. Right? So inside the chip, there could be scan. There could be a scan. Like I explained here, there could be a scan. And if your intention is to scan the test vector into the chip, right, through the TiDi, and then scan out the data. If you want to do that, that is the in test mode. Or it could be that see, this is not possible when we are doing in-field testing, etc. Right? Usually, the customers don't know where the scan chains are, etc. Right? We don't. I mean, the chip vendor will not explain that these are the scan chains. That information is not given to the customer. The customer may be told about, if there is a self test supported in the chip, the customer will know how to activate the self test. They would give a protocol and say, first you have to initialize, a particular register using your TDI, TDO, right? And then you have to give an instruction. See, that is the reason for this instruction, right? This instruction register may help you to start the test. The test could be a scan test, or it could be a logic based, or it could be a memory based. So that is that test instruction. Okay. So you may want to bring in a particular instruction saying, look, I want logic bits to be executed. And there could be many logic based controllers in your chip, because you may have a CPU, you may have maybe another CPU and memory. So you may want to activate logic based on chip 1. I'm sorry, logic core 1. So you'll have to bring a particular instruction and say, hey, start your logic bist, right? And when the signature is ready, that will be scanned out to see whether there is a bug. Similarly, there may be another mode where you are testing the second logic core, and another mode when you are testing the memory core, right? So that will all be done by your boundary scan. So this is how the internal test will work. So once again, uh, you will use this path, right, to sort of scan in the required patterns into the scan cells and things like that, right? So there could be many scan registers here, okay, and we can initialize them. And once the scan testing is done, you may want to follow this path in order to scan out the contents of the flip flops to see whether they have a error there or something. So there are other modes, but I don't want to go into all of them because that is a lot of detail, right? So please feel free to find, this is very well documented, right? So you may want to go through these documents. This particular, I will give you the link if you want, but it is easy to find it on Google. So feel free to go there and check out that particular. It's a very, some 150 slides are there, right? I only am showing you the most important ones. So JTAG's original purpose was, testing. That is testing of the chips and testing of the interconnects and so on. But nowadays they also use it for debugging, right? Maybe you have used it already. Some of you may have carried out projects on embedded systems and things like that, right? Some of you are hobby electronics guys, and you may have gotten some Raspberry Pi or some MSP 430 launchpad or something like that, right? So it is common for these target boards like Raspberry Pi or your MSP 430 launchpad, etc., to have an onboard JTAG emulator. Okay. These are also available as standalone, but many low cost chips also integrate. See, the MSP 430 Launchpad, Raspberry Pi are very cheap, right? They cost maybe less than $20. So there is an emulator which is already in the chip, and here we have shown a parallel port being connected to the JTAG emulator. But in a low cost system, it may be a USB port, right? It may be a serial port. It will be slow, but many times that is more than enough for the applications that we are using. And here is your PC, and this has some sort of a IDE running on it, right? And on this chip, you may have a compiler for ARM running, and there may be a debugger for ARM processor, right? You may be able to bring a C program or an assembly program written in the ARM instruction set, and you want to see when it is running on this ARM processor here, you may want to see what are the contents of the registers. You may want to put a breakpoint and read out the contents of the register and display them here and things like that. So JTAG is very useful here also, right? Because it has ways to shift in instructions into your processor boundary scan of the processor, and that instruction set could be something like, I want to know the content of a particular register, right? So ARM will respond to that instruction and place the content of that particular register on the bus, and this JTAG could read that and supply it back to the PC, and that will display the value of a particular register or a memory cell. See, there may be embedded memory on this ARM, and we may want to find what the value in that memory is, because we are trying to debug some software on this. So this is what is called as an emulation, right? So JTAG has been extended to be used as in the emulation, and that is a very popular application of JTAG. So I have shown the same thing here. So if you are taking a low cost board like MSP 430 Launchpad, so that comes with a USB port, and you can use the USB to, so it will be slow. The data will start travel one bit at a time, but that is it's a low cost board, so we can't afford to put a big parallel port and all that stuff, right? But if you are doing a much more complex system that you want to debug, then you may have to go for a more expensive JTAG emulator, which is usually available as a standalone product. Okay. Any doubts about boundary scan? That's all I'm going to say about boundary scan. Okay, so now we'll go to the next topic for the day, right? Today I want to cover two topics. So the next topic is analog testing. Okay. So in all our testing so far, when we were doing scan test or logic based, we have assumed that these chips are mostly digital, right? But analog circuits are also very important, right? We have lots of different kinds of analog products which are available. And by the way, these slides also I have borrowed from Professor Vishwani Agarwal, and he could be a student of Professor Vishwani Agarwal. I don't know who he is, but I borrowed these slides from them. So, like I was saying, there are different kinds of analog ICs. We have operational amplifiers, right? And programmable gain amplifiers. That means we can set the gain by selecting a code, right? That is why he says it's a mixed signal, because the gain can be controlled by a digital input. There could be active filters and passive filters, like we may have low pass filters, band pass filters, etc. Analog comparators. Again, analog comparators could be mixed signal, because the inputs are analog but the output is digital, which is a 0 or a 1. Then there could be a voltage regulator. Then there could be a mixer, which is useful in you may have come across mixers in communication circuits. Then analog switches, which may be useful in analog multiplexing. Then A to D converters, which are mixed signal circuits, right? Because they take analog input and convert them into digital format, or digital to analog, or phase lock loops, which are useful in creating, you know, clock signals and things like that, right? So we may have a lot of different kinds of analog circuits. It is not easy to integrate analog circuits into the same, the digital circuit, right? So many times analog circuits are still manufactured as analog circuits, but sometimes you do see some mix, you do see integration of analog and mixed signal on the same chip. This is more common in microcontrollers. So for example, if you see a microcontroller like MSP430, that has got A to D converters, D to A converters, it may have comparators, it may have some op amps. All of them are integrated into the same, along with the CPU. They're all integrated into the same chip. RF is another ball game, right? The radio frequency systems, right? These are popular in communication, uh, electronic communication applications like 5G and so on, right? So there, people may use RF amplifiers, which can be of two types, namely low noise amplifiers and power amplifiers, right? So, for example, if you have to send the signals out into space using an antenna, you may require a power amplifier. Similarly, the weak signals that you receive from the antenna may have to be amplified using a power amplifier. And you may also have, just like we saw analog mixers, you may have RF mixers, some oscillators, filters. So there are a lot of RF ICs may be required in order to build a communication system. These work at high frequencies, at the radio frequency range, right? There may also be those which work at the intermediate frequency range, such as variable gain amplifiers or programmable gain amplifiers, modulators, demodulators, filters, and then there may also be A to D, T to A converters, and it is also may be required to integrate some digital signal processors for communication. I'm sorry, for performing certain signal processing, right? After all, when we receive data, right, we may have to do many things with that data. So first we have to convert the data from analog to digital, and then in the digital domain we may do a lot of things. So it is very common to find a digital signal processor. See, for example, all the beam forming and things like that, they're all done by the digital signal processor. So compared to digital logic, testing of analog and RF circuits is much more harder, right? Mainly because you would need all kinds of equipment to test analog and RF components, right? In digital, you see, we have waveforms which are simply zeros and ones, right? See, if I have this digital data, okay, so I will, look at them as 0 1 0 1 or something like that, right? I'm not interested in the actual voltages and things like that. So there is such a thing as a threshold, right? And as long as the signals are, above some value, we are sure that it is a one, and if it is below some value, we'll assume it's a zero. So, as a result, digital signals are somewhat easier to handle. But analog signals, the exact waveform is important, and exact voltage level is important. Noise is definitely something that we want to look at, right? Whereas here, that noise is not important to me. I can easily, in fact, get rid of this noise, right? It's a very simple circuit that can eliminate this and produce a clean waveform, right? But I can't do that if it's a bad sinusoidal signal. See, suppose I'm getting this as a sinusoidal signal. See, it has a lot of noise. It has a lot of problems, and it may not be so easy to eliminate all those problems and make it a pure sine wave, right? All kinds of filtering, etc., are required, right? And in digital logic, we had a nice stuck at fault model, but here there is no such thing, right? And if I have a faulty, suppose this was the sinusoidal is coming from a some sort of an oscillator. Okay, imagine that we have made a oscillator like Colpitt's oscillator or something like that, right? And it is supposed to produce an analog waveform, the sinusoidal waveform. But every fault will cause a different impact on that sinusoidal waveform, right? So it's not that there is a suck at zero, suck at one kind of a thing, right? So that is a problem. So precise modeling of faulty behavior is not possible, and different components need different fault models, right? If there is a resistor, it may require a fault model. If a capacitor, another fault model. If it's an op amp, another. So it's very difficult. So the actual amount of area that analogs occupy, right? Most of the, I think I may have mentioned this to you earlier. A large portion of your chip is actually memories, right? And then digital logic, and a very small portion of it is actually analog. But from a testing point of view, they cost as much as the rest of the chip. Okay. So the traditional way of testing analog ICs or analog circuits is to apply lots of different waveforms. So these may be the signal generators. It may be a DC signal or a sinusoidal signal or some noisy signal, etc. And we should be able to select one of these. And the output of the analog device, right? We may have to filter or we may have to take it directly, and we may have to make a lot of different measurements. Whether it has a DC component, is there a RMS value that we need to read, or the peak value, and so on and so on. So you can see that it is highly measurement oriented. Okay, see, analog ICs are somewhat measurement oriented, the testing of analog ICs. So typically, what they will do is, as you can guess, we may not be able to really do, all this characterization tests, right? Thorough tests on every device. It's not possible, right? So they will do this during characterization when we get the samples from the IC, from the fab. That is when they will understand the process and so on, right? Later, it is easy to apply. Analog ICs may also have structural issues, right? I mean, there may be of course, analog ICs can also have open wires, right? Or they can have short circuits. The good thing about analog ICs is when they happen, it's very easy to tell. See, this oscillator, those who have done experiment on Colpitt's oscillator, right? How many of you got that Colpitt's oscillator working in the very first attempt, right? You struggled, right? So any fault, the oscillator will not oscillate, right? So that way, it's very easy to eliminate bad ICs from good ICs, right? But if the ICs are quote unquote good, meaning they do generate sign, right? But then are they good enough? Meaning, if there is a spec that is given to us, are they within that specification? That is the harder part. Okay, I hope that is clear. Structural faults are very easy to catch, but once the structural faults pass and we have parametric faults, like maybe the frequency that we were supposed to get is 10 megahertz, but maybe we are getting slightly higher or slightly lower, right? And there may be a specification which says that the oscillator frequency should be 10 megahertz or plus or minus 10%. So 9.9 megahertz is okay, 10.1 megahertz is okay, but anything not in this range may be rejected. We had to throw it away because it doesn't meet the data sheet specification. So that is the hard part. That is why we need all these measurements and so on. Okay. So in the analog testers, there are all these instruments, right? RMS measurement, peak measurement, DC measurement. All these are available as instruments on the your analog tester. So you may not be able to do that for every chip that comes out, right? You will possibly do structural testing very easily and remove the bad ones. And then sample testing may be one way of being able to be reasonable in terms of testing, right? So people try spec based testing. What is spec based testing? Does the IC meet the specification? For example, the bandwidth of this operational amplifier should be, let us say, 10 megahertz. Is it really 10 megahertz? Maybe it is not. Maybe it is only 8 megahertz. Similarly, there may be a spec for the offset voltage, and the data sheet will tell what the offset voltage can be expected to be in some range or some. output current will be in a certain range. So there may be a number of such parameters, and there are specifications for each of them. And spec based testing simply means make all the measurements and see whether they meet the specs. Okay, so you can see it's a big problem, right? How much measurement will be involved, right? So if you are a lab kind of a person, right? If you like labs, to work in labs, do experiments, then this is a very ideal job for you, right? You will enjoy being a analog test engineer. You will require a lot of different knowledge of different kinds of equipment like oscilloscopes, right, and the spectrum analyzers. Uh, so you will need to be good at instruments. The other way is what is called as model based testing, right? I mentioned to you about this catastrophic faults, that means structural faults, open faults, etc. So we can try to see whether we can eliminate bad chips by looking at these catastrophic faults in the circuits, or whether it is simply out of range. We the fault is so bad that it's producing very poor quality output. Then we don't want it. And then there is something called as alternate test. So this is the spec based test. So using the automatic test equipment, right? You will have to write a test program, right? The automatic test equipment has a language of its own, right, to program it, right? And you will have to write a program in typical languages that are used are C++, C hash, etc. Or I think nowadays Python also may be getting popular. So you write a program to make the ATE generate whatever waveform that you are interested in generating, and then apply that to the circuit and a test, take the output, and again the same test program will have to make all the measurements, and then see whether the IC meets that specification. And if it doesn't, note down that this particular IC is, failing. Okay, and then do it for the next sample. So this is all usually automated with the help of a test program. So here is an example that they have provided of a operational amplifier, and you can see that this op amp has been configured to work in the non-inverting configuration, right? So its gain is supposed to be 1 plus 4 or 5. 5 is the gain of this, in an ideal situation. But it will deviate a little bit because the op amp may not be ideal and all that, right? Or maybe the resistances have some tolerance and so on. So there may be a variation in the actual gain. It may be above 5, below 5, etc. So the spec may say that the gain should be in this range, and this should be the 3 dB bandwidth, right? And the signal to noise ratio should be this, but there is also an acceptance range. Similarly, input offset current, input offset voltage, output offset voltage, all these are given in the data sheet along with what is an acceptable range. So we may, in order to measure the DC gain, we may have to set up a, so in your test equipment, all these will be there already, but you have to make the circuit, right, using a test language, right? You will have to, just like in Spice you connect all the components using some language, right? In the same way you will have to make the circuit, and then you have to introduce a DC voltage and vary the input from, let us say, 0 to 1 volt, in steps of 0.1, and then note down the outputs. See, if it is a good op amp, then it's the output will go from 0 to 5 volts. Okay, the gain is 5, right? So that is what we expect, right? So a good circuit should produce 5 volts steadily. But maybe because of some op amps issues, right? um, Assume that these resistors are perfect. Okay, assume that these are high precision resistors. So ATEs will typically use very high precision resistors, right? So there is very little reason to believe that the resistors are not, the are not in the required range, right? So if we see a deviation from this expected output, it is possibly because of the op amp, right? So there is some op amp, let us say, which produces slightly less than 5 volts. Something may produce more than 5 volts also. So if it is within this band, then we are okay. We'll pass the device. But if it is going below that, then there is something wrong. Okay, this is a bad op amp. Similarly, for measuring the bandwidth, you may, instead of a DC voltage, you may apply a signal generator, sinusoidal waveform. Again, the ATE will have a very good sinusoidal waveform using high precision components and so on, right? And we can measure the gain of the AC waveform and increase the frequency from low to high. Maybe start with 1 hertz and go higher, and then look at the decibel gain and do like a what you would do in a AC analysis of a circuit. Okay, in a way you are exactly doing what the AC analysis will do, right? But on the real chip, right? So you will get a plot like this perhaps, right? At higher frequencies, the gain will begin to roll off, and we can find out where it's reaching the 3 dB point. And maybe there is an acceptance range, right? In this example, let us say anything with 90 to 110 kilohertz is acceptable. So 93 will pass, but 87.5 will fail. And I think if it is higher than 110, um, I don't know. I mean, why would we fail something like that? I don't know. But maybe, I'm not an analog expert, but I think having a very high bandwidth may also be a problem in some case. Maybe from a noise point of view or something like that. So at the end, they also talk about this alternate test. Okay, alternate test is like using of machine learning, right? I think somebody asked me the other day, is there any opportunity to use machine learning around? So in a way, they are doing that in this AC test, etc. I'm sorry, in analog testing, right? It is in the past. See, this presentation was made in 2012, so they say that it has limited acceptance in the industry. But now we are, machine learning is a sort of accepted thing now, right? So as a result, this particular method has gained popularity, right? And people from the colleges have been proposing this for a long time, right? So the essential idea is, see, the measurements are the ones which are difficult, right? Having so many different equipment for making measurements is what makes it all very difficult and expensive, and also error prone, right? See, when you use these equipments, if you don't calibrate the equipment correctly, or if you are using the equipment wrongly, everything is wrong, right? You need very highly skilled people to do all this characterization test, etc., right? So what could be done is, sorry, yeah. So what could be done is, make a measurement that is easier. Maybe one thing only we'll measure. Maybe in the example of the op amp, right? Maybe the power supply current could be the measurement that we could make. Right? So there must be some relation between the bandwidth of the op amp and the power supply current. Some correlation will be there, right? Similarly, the gain of the operational amplifier and the power supply current, there is ought to be some correlation. Okay. So we will measure that current, which may be an easier thing to measure, right? And as a result, the number of different measurements that I may have to make may be limited. And then there is a regression model that we could build, which relates that measurement of the current with the measurement of the other specifications like bandwidth and offset voltage and things like that, right? And this regression model can be used to sort of classify the circuit, right? You know that machine learning can help you in classification, right? See, for example, if you have a lot of data points, right? The machine learning classifiers can help you, differentiate these points, and they will put them in different bins. Right. In this example, maybe we only want two bins, good and the bad, or there could be multiple bins, right? Depending on how precise uh, the analog circuit is, right? So here is the example. So we can try to relate DC gain and input offset current with the supply current. And the DC gain, the spec is it should be between 4.9 to 5.1, whereas the supply current is in the range 3.8 to 4.1. So this is something that you'll have to have a, when the gain is 4.9, the supply current is 3.8, and when the gain is 5.1, the supply current is 4.1. So this is something that you have to establish through a lot of experiments. So data is very important. So how did I come to know this? I mean, you have to do the experiments. Similarly, the input offset current minimum is 300, maximum is 520, and the corresponding values of the alternate measurements of the supply current may be these, right? So this is something does that requires a lot of experimentation. Then you can build this data scatter plot. Okay, so on the x-axis is the supply current, and on the y-axis is the DC gain. And when you build a scatter plot, perhaps there is a way to draw a line somewhere and say, this is our regression model. Okay. And we may be able to write a, these are the acceptable DC gains, and as a result, this is the acceptable IDD range. Okay. So this is a simplistic example where we have only two things. One is the current, and the other is the gain. But as you can imagine, in a a complex device, right? There could be so many things, right? There could be multiple things that we are required to measure, right? And even if you can do a subset of them, maybe you can use regression to classify. So they did this experiment, I think, in their lab, right? They took some 300 devices, and out of those 300 devices, I think 195 were known to be good, right? Maybe using some other test method. And they say that 185 of them were passed by the alternate test. Okay. So the alternate test was stricter. So it failed some of these, which are actually good. So as a result, there was an yield loss. Okay, about 10 ICs out of 300 were failed. So that is what could happen, right? So this is not so bad. I mean, it's better to be on the safer side, right? To err on the safer side is a better thing to do. But if the yield loss is very high, then maybe you will not get a very good response, right? People will not be too happy because you are being very strict and rejecting even good chips. Similarly, this is the output input offset current. Okay. Again, this is the supply current and this is the uh, offset current. So you can see there is a much wider range here, right? So as a result, the classifier may not reject too many chips, right? So you can see that in this experiment for offset, based on the offset current, uh, out of 300, 299 were good. Okay. See, the gain is, this lot of things will be considered as bad, right? So that is what this means. Out of 300 parts, a lot of them failed because they were not meeting the gain criteria. But because this offset current, there is a wider acceptance. So the number of good parts are out of 300, let us say 299, right? So here also the alternate test only passed 270, and as a result, 29 ICs were rejected, and that resulted in a yield loss of 9.67. Okay. This was in 2012, but given that now machine learning is a much more advanced field, I would think that the much better results will be possible. And I told you about the IEEE 1149.1, which is a boundary scan standard, or the JTAG. By the way, JTAG stands for Joint Test Action Group. Okay, so this was the name given to the committee that was set up to define that standard. So different companies had representatives who got together to define that standard. That committee was called JTAG. They also came up with a uh, some sort of a standard for the analog test bus. Okay, so because nowadays analog signals are also being, I'm sorry, analog parts are also getting integrated into your chips. So there may be mixed signal, analog, digital, and so on, right? So if a mixed signal chip has to communicate with a some sort of a discrete component, right? Maybe, and so on, right? So there could be a lot of different kinds of analog signals that may have to travel through um, the the PCB, right? So they have defined a standard called the analog test bus, and it is somewhat similar to your boundary scan, except that it also allows you to send analog signals. The analog signals can travel, and come to the other. So it also has the same kind of idea, right? And there is another kind of a testing that sometimes is used, It's called loop back testing. This is practical when we have both, let us say, DAC and ADC. Our intention is to test the DAC and the ADC. So what can be done is we could set up some sort of a counter or something like that, and give the inputs to the DAC from the counter. I'm sorry, here. Okay, this is a counter. The counter is giving the input to the DAC, and the DAC is generating an analog signal. And normally, this ADC would take the input from some other analog circuit, but now in the test mode, it will take this signal coming from the DAC and it will convert it into digital format. So if you had used a counter, then the output of the ADC should also generate a count output. If it is generating anything else, then there is possible, that there is a problem. Okay. So that is what is the loop back testing. Okay. So I believe that is all I had to cover today. We still have some time. So if you have questions, I'll be happy to answer. Okay. So what we have talked about today is we talked about boundary scan cells. We talked about digital design testing using boundary scan, and we briefly talked about analog testing. And I mentioned that it is often a very difficult thing to test analog signals because they have. So let me maybe quickly show you some. So we can go and do some LT spice maybe. So you may already have LT spice loaded on your machine. So you can do this when you get time, right? So they do provide a lot of examples, right? And let us try one of these. So let us say there is some audio amplifier or something like that. Okay, so this is the circuit, right? And everything is already set up for you, so you don't have to work very hard, right? So you can just simulate this circuit, right? And then you can observe the waveforms at different points. So let us assume that this is the output or something like that. So look at the output waveform. It is the amplified output, I guess, right? It goes from 0 to minus 7 and plus 7. Okay, that is the waveform. It appears, at least to the naked eye, it appears like a purely sinusoidal waveform, right? So you can see what waveform will be generated if, let us say, we make certain changes. See, for example, what if let us say this wire was broken. Okay, so let us say this wire was broken, right? Then obviously the output will be very different. So you can see that it is now going from 7.7 to 7.9, and it is not looking so good as a sinusoidal, right? It is somewhat like a what do you call it, the half wave rectified kind of output is coming, right? So the range has changed. Earlier it was from minus 7 to plus 7, now it has changed. So this is what I meant by this is a bad fault. It's a structural catastrophic fault. Okay. So that is causing a very bad output to be generated. Similarly, maybe we can try, what if let us say this resistance was removed, right? And see what happens. Again, you can see, right? It completely changed. So I would think that eliminating this will be very easy to do. On the other hand, if the parameters are different, okay, see this resistor is 200 ohms, but if I assume that it is 230 ohms, right, then simulate it, right, then let us see how the circuit behaves, right. There is maybe a marginal change. See, I think this value has gone up a little bit. Okay. Now the output is 7.43 volts maximum, or 7.36 volts, right, or something like that, right. Let us put it back and see what happens. Yeah, let us. I have undone that change. Okay, I don't remember which one the output was. Okay, so everything has been undone. So now let us see. So yeah, indeed. See, this was slightly higher, right? It is when that resistance was lower, like this one. I think I changed this guy. So when I made a change in the resistance, this the output was there was an influence on the output, right? uh, and unfortunately in general many things may happen, right. So maybe all the resistance have some tolerance and they may change, and similarly there are some capacitances, they also have some tolerance and they may change. So we may have to observe, you know, then when the we cannot eliminate them so easily. Okay, they will all look sinusoidal. So the two examples that I gave, where one was the output was 7.0 and the other was 7 point something 4 or something like that, there the spec will come into play. If the spec says, accept it, then you will pass the IC. Otherwise, you will fail the IC. Is that clear? Any questions there? Let me see if anybody is asking any questions in the chat. Okay. What specs test do we exam? What specs test we do example means what? Specs are like I showed, no? The specifications may be the input offset voltage, output offset voltage, gain. All these are open loop gain, bandwidth. They're all specs. How to remove faulty condition is both digital and analog circuits. See, again, that is not our problem. You understand? The course on testing, right, is meant for people who are interested in testing. Okay, we can reject the bad parts, and then it goes back to if they find that a large number of them are defective, right. See, first of all you should understand that nothing can be done about the defective parts. We can't repair them. If that is what you are asking, no, we cannot do anything. We have to throw them away, right. If it is a PCB, then uh, in the old days, I think the PCB, they used to mount the ICs in sockets so we could replace the IC. But presently, I don't think they do that. They directly mount the IC on the socket. So when an IC goes bad in the PCB, replacing the IC is also not so easy, right? So it may have to be sent back to the the company where they may be able to remove that IC and solder a different one and things like that. Usually they will replace, if it is in the warranty period, they'll just give you a new one, and then later they may want to fix that PC. And if you want to understand what is the real cause why this fault took place in the first place, that is not easy. You will have to do a lot of hard work to diagnose the problem. If the device failed alternative test, then how do we know it is actually good or not? No, we don't know. We don't know. We may we are welcome to do a regular test. Okay. The alternate test has been proposed as a low cost test, right? So it's like you go to one doctor and he says, you have a problem. You go to another doctor and he does a different test and he says you are okay, right? Now, do you trust this new doctor who did a different test, and that is your choice, right? Can you explain JTAG emulation? JTAG emulation means, see, we already know that JTAG can, scan out the contents, send a test to the device and the test, and the response it can scan out, right? The response, if you can scan out response, you can also scan out the contents of registers and memory, etc., right? So that can be useful in debugging, that's all. So instead of testing, what we are doing is we are debugging, right? Software debugging. For example, I may have an instruction that puts the value. Let us say I suspect that the add instruction, right, which was supposed to set a particular flag. I don't know, there is some bug there or something like that, right? So before the add instruction, you want to put a breakpoint, and then you may want to initialize those registers that are part of the add instruction. And then at the end of the add, you may want to scan out the content of the sum and all that, right? So you need a way to put proper values in those registers, that you can use JTAG for that, and then scan out the contents of the sum register. That can also be done through that. Faults test apply on complete circuit or some part. The testing is done if there is a large circuit, okay, let's say large digital circuit. Then if you are doing scan testing, um, it is possible that you have your scan chains are cutting across multiple IPs. See, that scan chain may go from a processor to another DSP and all that kind of stuff. But it is possible that you isolate it only for one particular IP. So that is your choice. See, these are not real. There is no hard and fast answer for these questions. Okay, it's all your choice. You understand? So that is what the engineers do for their living, right? They can change things if they want to. They can say, look, I only want scan chains to be meant for the processor, microprocessor, or I want separate scan chains for the DSP, like that. So it's their choice. Okay, any other questions? We still have 5 minutes. Rohit Kumar, could you cover SSH? How to test? What is SSH, by the way? How to test complete chip circuit under test pattern generation? So huge computation time. Yes, it takes many seconds to test a big chip, but that is required, no? So, what is SSH, Rohit Kumar? Packet based testing method. I don't know what it is. I have not ever come across that. Where did you come across packet based testing? Is it for communication circuits? I don't know that there is such a thing which is, yeah, but it may be meant for some communication specific circuits, right? I have never seen anything like SSH, right? If you have come across it in some paper or something, was it related to communication, digital communication? Go back and check. Okay, are they talking about packets in the context of communication or something like that? So, streaming scan network Siemens. Okay, I don't know. See, this may be very company specific thing. Um, I don't know what it is. Streaming scan network Siemens. I will try and see whether I can find out something. But sometimes you see companies also come up with some fancy names for all these things. So I need to know whether it is a radically different test method or is it just a nice name for another known technique. You can also do that. See, why don't you find out some papers on streaming scan network by Siemens? Usually you will find them. They will give you a lot of literature. They may not give you too many details, but at least they will explain the uh, basic concepts in some sort of a white paper. So, see, all of you should now begin to understand that there will be a lot of things, right? In any course that you take, right? Anybody can only teach the fundamentals, right? There will be a lot of stuff that we cannot teach, right? In about 40 hours, there are many people who are coming and giving you, an overview of all the topics. They will not be able to cover every subject under testing. Okay, and learning never stops. Okay, in another year, lot of new things would have been invented, right? So we cannot say assume that everything will be taught to us in classes. Okay, so you should make it a habit to follow the literature which is available online. The good thing now is the literature is available. Okay, see, earlier everything was printed literature and it was very difficult to get hold of these things, but now they all put it online. So it's not too difficult to get hold of literature. Some conferences that you could follow are the international test conference. So if you see a paper in international test conference on this SSH that you talked about, right? So you can try and read that paper, right? So Pinky says very new things are there. What is okay? Yeah. Any others? Okay, then I will see you tomorrow. Any link for material? I will definitely give you the PPT that I created. If you want a link for that, the two sources which I used, I can give it to you. That is not a problem, right? I can give it to you. I will put it in that paper itself. For
Uh,
practical. What do you mean by practical? For lab or something? Oh, okay. See, if you want to build a lab for testing, you will need some equipment, right? If you want to use tools, see, unfortunately, you may not find public domain tools for test. Okay. So things that you could do in your college, maybe, see, the lab view may be a good thing to use, right? Or Keysight, okay. But that requires you to purchase those tools, or the hardware that they provide. Okay, so NI LabVIEW may be a good thing to do, right? Um, Tools, like I said, Professor Aditya, there are no. See, if you want to look at ATPG tools, etc., you will not find, right. These are expensive tools that you get from EDA companies. You may not find free tools like that. Some universities may have made them available. You will have to check, right? I have not come across many of them, right? Um, so, but with whatever you learned here, see, I have shown you how Verilog simulation tools are available, and you may be able to use them, right? I have given you examples of how. I don't know whether you saw the exercises that I gave, right? So a number of these could be done. See, S27, right? That itself is a pretty decent sized example. It will take several hours for the students to do that exercise. So you can try creating such exercises for the lab if you really want to teach a test lab. Synopsis and Cadence have all the tools. If you have access to Synopsis and Cadence, by all means, go ahead and use those tools. But I thought you were asking for public domain tools. Professor Aditya, the easiest way is for you to go to their website, Synopsis and Cadence, and search there for their DFT tools and ATPG tools, right? Share the tools, and Madam Naga Vijaya Lakshmi, right? You should not be asking these questions to me, frankly, right? You should be able to find them. No, why this in this day and age you are asking me to name the tools and so on, right? Everything is available online, isn't it, madam? Mm. Scripting languages. They usually use. I think nowadays Python may be popular, and also maybe TCL scripting languages. Okay. See, if you are planning to include these things in your class, frankly, even without this, see, I never had test EDA tools, etc. when I was teaching in IIT Delhi. Okay, you can ask the students who took my classes. We used to teach on the board. There was not even all this technology like projection and all that kind of stuff, right? So there is nothing wrong in that, right? The idea is for us to make sure that they get the concepts, right? Sorry for me, sorry if I'm being very blunt and a little harsh, right? uh, we don't have to always say that cadence tool is not there with us so we can't teach. Nobody expects you to use these tools in the colleges, right? See, the textbooks were written. See, if you see textbooks on testing, they are not talking about tools at all. They are trying to tell you how the concepts are done. What is scan? What is logic based? What is how does a PRPG work? You can create your own exercises if you want to use with simulation and all that. Right? It is wrong to keep on saying that. I found it in the previous class also. Right? People were asking me, tools we don't have and all that. Frankly, you don't need. If students are pressurizing you to about tools, you try to set up challenging exercises for them on what free tools are already available. Right? we should see what is available rather than what is not available. Is that okay, ma'am? Professor? All right. Any other questions? Okay. Thank you very much. Bye bye. I'll see you tomorrow.
Thank you so much, sir, for your time and for sharing such insightful thoughts. It was a pleasure having you as our speaker. Sir.
Thank you. Thank you.
Thank you, sir.